This lecture will look at voting schemes a little more closely, and the main message of this segment will be that even very reasonable sounding voting schemes can run into problems. And we'll do it by a series of examples. We'll look at situation. I'll ask you to pause the video and think about the situation, and then we'll to continue when you're ready. So let's get started. Let's start with the Condorcet condition, which on the face of it is incontrovertible. And consider the following examples. So here we have 1,000 agents, and here are their preferences. So for example, 499 of them prefer A to B to C, and so on for the others. First question is, not every voting situation has a Condorcet winner. Does this one have? So it's a good time for you to pause the video and think about it. Well, the answer is yes. There is a Condorcet winner, and it's B. And why is that? Well, let's look at the relative preference of B to A and the relative preference of B to C. Well, we have here that 501 of the agents prefer B to A, and 502 of the agents prefer B to C. So clearly B is a Condorcet winner. Well, so where's the problem? Well, now think about the simplest sort of voting we're familiar with, plurality voting. Everybody votes for their top candidate. Who would win the plurality voting here? Well, again, you could pause the video, or in this case, it's fairly straightforward, right? Clearly, A would win it because 499 agents would vote for A, and the next highest number would be C with 498. So plurality voting doesn't give you the candidate that on the face of it is the should be the clear winner. What about voting plurality with elimination? So this might take a little more time to think about. So you might want to pause the video here just for a second. And now when you think about it, you see that C would be the winner under plurality with elimination. And why is that? Well, you'd first run a plurality, and you'll see that B is the loser, so B would leave the competition, if you wish, and now it'll be head-to-head between C and A, and in this case C would be the winner because 501 out of the 1,000 agents prefer C to A. So C would be the winner. And so two voting schemes, both of them on the face of it reasonable, would give you different answers, and both answers different from the criterion that on the face of it seems quite a safe criterion, namely the Condorcet condition. So here's another example, and let's think about what would happen in this case. What would happen under plurality voting? Well, clearly under plurality voting, A would win, since A would get 35 votes, and the second highest would be B with 33. What would happen under the board of voting? This takes a little more thinking, and you might want to pause just for a second the video. But when you continue, by that time you'll quickly realize that, again, A would be the winner under Borda. And clearly you have A, B, and C each appearing in each of the places 1, 2, and 3, with A appearing with the largest number of agents in the higher locations. So A would have the highest Borda count and would be the winner too. So this looks very good. But now what happens if C drops out? So C realizes that he has no chance of winning the election and drops out. Now what would happen under the both plurality and border? Just, you might want to pause for a second the video and think about it. And when you do, you realize that in both cases, B would win. And so here you have a candidate that has no chance of winning, and his sole role, if you wish, is to change what otherwise would be the outcome of the elections. Here is another peculiarity of voting schemes. And imagine that we're doing pairwise elimination. That is, we're going to take one candidate, compare him to another, take the winner, comparing to a third, and so on and so forth. So the order in which we compare the candidates, we call that the agenda. So somebody needs to set the agenda. We call that person the agenda setter. So imagine pairwise elimination with the order of comparison A, B, C. In other words, A will be compared to B, and then B will be compared to C. So who would be the winner of this election? A good time to pause the video and think about it. And once you do, you realize that C would be the winner, because when A is compared to B, well, we have B preferred to A by a majority of the agents, so A would be eliminated. And then when the winner, namely B, is compared to C, you'll see that C is preferred to B by the majority of the agent, and therefore C will be the winner of this election with this ordering. What happens with another ordering, like ACB? Again, you might want to pause the video, and by the time we resume, you'll realize that in this case B would be the winner. And perhaps not surprisingly, when you ask about the third ordering, BCA, you'll see that A would be the winner then. And so it's a little perhaps disconcerting that the same voting scheme, merely by deciding on the order in which you run it, will lead to very different results. And here is another example. There are 3 agents and 4 candidates, and the preferences are as written up there. Now, consider again pairwise elimination with the ABCD ordering. And what would you get? Again, pause the video for a second, think about it, and realize that the winner would be D. What about this case? We're now not talking about different orderings. We're talking about a given ordering and an outcome, but there's something a little troubling about this outcome. What is it? Okay, pause the video, think about it, and realize that the problem is that everyone prefers B to D here, right? So B is preferred to D here, B is preferred to D here, and B is preferred to D here. And yet D, this Pareto-dominated candidate, wins. So something is wrong in this picture. Well, the goal here was not to give us the final answer what is the right way to vote. In fact, that is not well defined. The goal was to alert us to that the fact that a lot of reasonable sounding voting schemes can be problematic. And so with this note of caution, we'll finish this segment.
This video is going to tell you at a high level probably the most important and surprising thing that we have to tell you about social choice, which is that it's impossible to come up with any social welfare function which is sensible in a particular formal way. So first of all, let's remember what a social welfare function is. A social welfare function is a voting rule where every agent tells me a set of preferences. So it gives me a total ordering over all of the choices that we have to make, over all of the candidates. And getting this whole set of different rankings from all of the different agents, the social welfare function gives me back a single ranking, which is the social choice. So think about voting over a set of candidates. Everyone has preferences over all the candidates that we're going to vote over, and getting back a single ranking that is the kind of aggregate ranking for all the agents. So what would we want such a ranking to do? What would it look like for such a ranking to do a good job? Well, here's one thing that seems pretty obvious that such a ranking function should do. We'll say that a social welfare function W is Pareto efficient if any time it's the case that all of the agents agree on the ordering of two outcomes. If everyone thinks that candidate A is better than candidate B, then the social welfare function also agrees about that part of the ordering. So it might say all kinds of other things about candidates C, D, and E, but if everybody thinks that A is better than B, then the social welfare function also is going to tell us that A is better than B. It's going to put A somewhere higher in the ranking than B. So, and that's all we're requiring by Pareto efficiency. We're just saying only in the case when everybody agrees, absolutely everybody agrees, the social welfare function has to rank in the appropriate way. A second thing we might want is what we call independence of irrelevant alternatives. So we'll say that a social welfare function is independent of irrelevant alternatives if the way that I rank between A and B only depends on the way that all of the individual agents ranked A and B. So if I want to decide in the social ordering how it is that I compare A to B, I should do that only by looking at how all of the individual agents relatively ranked A to B. So I shouldn't care about how everyone felt about A and C or about B and D. I should just look at the A-B rankings for everyone, and that should tell me how the social welfare function ranks between A and B. Finally, I'll say that a social welfare function has a dictator if there exists a single agent whose preferences we always just return as the social ordering. So in other words, if I've got n different agents and they always give me some kind of ordering, and I just say, you know what, I only care about agent 3. Everybody else, it just doesn't matter what you tell me. I'm going to throw it in the garbage. I'm not going to think about it at all. I'm just going to give you back agent 3, and I've decided in advance who agent 3 is. It's always going to be the same guy. That's what it means for a social welfare function to have a dictator. Now, it's kind of terrible for a social welfare function to have a dictator because it means that it's not aggregating in any meaningful way. It's just always reporting back what one person thinks. Notice that a social welfare function that does have a dictator trivially satisfies independence of irrelevant alternatives and Pareto efficiency, because Pareto efficiency says anytime everybody agrees, the social welfare function has to do the right thing. And when everybody agrees, in particular, the dictator also agreed. So we would get Pareto efficiency for free. Likewise, we would get independence of relevant alternatives for free because we're only going to care about the dictator's A-B rankings in order to decide the A-B ranking. And so we're not looking at anything else from any of the other agents. So we see we can satisfy our two properties from a dictatorial social welfare function, but dictatorial social welfare functions are pretty undesirable to us. Well, here's the punchline. Kenneth Arrow in 1951 famously proved the following theorem. Any social welfare function over 3 or more outcomes, so candidates in elections that have more than 2 candidates, that is Pareto efficient and independent of irrelevant alternatives must be dictatorial. So in other words, these two things that seem very natural that we would want, Pareto efficiency and independence of irrelevant alternatives, are so constraining on the set of social welfare functions that they imply that we would have to have a dictatorial social welfare function. Since we can't possibly live with a dictatorial social welfare function, what that really means is that we have to give up either Pareto efficiency or independence of irrelevant alternatives. And that's pretty bad news because these are both pretty natural things.